Hello, my name is Eric Severson, and I'm going to be talking to you all today about the message complexity of population protocols. This is joint work with my co-authors David Doty, Masa Eftekhari, Talia Amir, and James Ausnes. Now, the original population protocol model considered a population of anonymous finite state agents. So for example, here we have two states, L and F. And the agents update via asynchronous asymmetric interactions. So the agents meet in pairs, and the pair of agents updates via some transition rule. So the protocol is defined by a rule delta. In this case, whenever two L's meet, one of them becomes an F. And all of the other interactions are actually null. Nothing changes. Now, in order to talk about time complexity of this model, we consider a uniform random scheduler that picks a random interaction at each step. And every n steps we consider to be a unit of parallel time. So parallel time is proportional to the average number of interactions that agents themselves have. In this case, for this protocol, it'll actually converge to having a single L, and it'll take linear amount of time. So this is solving the problem of leader election. Now, the original model had some key limitations. Among them were that there were time lower bounds were developed for very fundamental tasks, including leader election. So it turns out there's actually a linear lower bound for leader election. So in some sense, this simple protocol is actually optimal. You can't do any faster in the original model. Also, the computational power was limited to only computing semi-linear predicates. As an example, the majority problem of detecting if the number of x's is greater than the number of y's is semi-linear. But a problem like detecting if the number of x's is greater than the number of y squared is not semi-linear. Now, recent results have been expanding the model and allowing a greater state space in order to get around some of these lower bounds. They've been able to achieve faster leader election protocols, faster protocols for solving the majority problem, and also efficient protocols for the problem of population size counting, which only even makes sense if the state space can grow with n, since the agents need to know the answer. Now, for a simple example of how large state spaces help protocols be more efficient, let's consider a large state majority protocol. So the goal is to detect in the initial population are the red or the blue agents in the majority. Now, our state space is going to be integers ranging from -c to c for some constant c, and the initial states are going to be -c if they're red and +c if they start blue. So in our example here, we have 50 red agents, 51 blue agents, c is 202. And the update rule is just to do averaging. So it's a discrete average given by the floor and ceiling of their average. And then the output they produce is the sign of their state. So if their state is positive, they think that blue's the majority. Negative, they think that red's the majority. And here we can see a simulation of what this update rule will do. And relatively quickly, it converges to every agent being blue. So they've all decided that blue is the majority, which is correct. And it can be proven that the states will always reach 3 consecutive values in log n time. So in this case, they're all the values 1, 2, 3. And thus, if we set the constant c large enough, we'll actually get an exact majority algorithm that takes log n time. Now, our work considers a new definition of message complexity. So these protocols that use large states also are incurring a larger communication cost, because in the interaction between two agents, the transition function is a function of both of their states. So we propose a refined model that distinguishes the interaction communication complexity from the local space complexity. So we can think of now the state of an agent as being 2 parts, a message set M and an internal state I. And when the two agents interact, their update rule for the first agent is a function of its local state, its message, and the message it receives. Likewise, the other agent sees its local state and the message it receives. So we can view the original model as having both constant states and constant messages. And more recent protocols have been using super constant states, but also super constant messages in their interaction. And we, in our work, focus on an intermediate, having only a constant number of messages, but still allowing super constant states. So this is an intermediate model between the two, and we seek to ask how powerful it is compared to the more restricted and less restricted models. Now, it's worth noting that existing protocols that use large states are also using large messages. And the rough idea of how that tends to work is their large state space comes from a set of integers that has some super constant range. For example, in our majority protocol, that was integers from -c to c. And in their interactions, they somehow compare those integers. So here we took an average. We might also take a max instead. In other words, the message, though, they need to send is roughly the same size as their whole state. In addition, most of these protocols are non-uniform. They somehow rely on an estimate of n. Here, we needed the constant c to be at least as big as 2n. In our work, we instead focus only on uniform protocols. So our transition function is independent of n and has to work for any possible population size. Now, if we allowed non-uniformity and had an estimate of log n, there's a standard technique called a leaderless phase clock we could use and achieve more powerful results with constant messages. But we do not give ourselves that power in the work we consider. Now, the first problem we consider is the question of computability with constant size messages. So we ignore time complexity for the moment and just ask what the model can compute. And this previous result gave a formal model of super constant state uniform protocols. And it found the computational power varies with the state size. As soon as the states are polynomial in n, you can actually simulate a Turing machine across the entire population. And thus, the computational power is a Turing machine whose space is equal to the memory of the whole population. However, if the state set is sub-logarithmic, if it's little o of log n, you can only compute the semilinear predicates. So it's exactly as powerful as having constant size state set. Now, in our work, we find a similar characterization. Again, if we have a polynomial size state set, we get the same Turing machine simulation and thus the same complexity class. However, as soon as the state set, again, this is the internal states, are sublinear, then with constant messages, we can still only compute the semilinear predicates. Now, the idea for how the first result works is it's based on a slow simulation of large messages. So if our state set is big enough, we can actually simulate having big messages. And the idea is we can have two marked agents that simulate one interaction at a time. So every time they interact, they send a few bits. The other interactions are null, and they interact again and send a few bits. So this is going to incur a very big slowdown, but we can simulate big messages. However, to get this to work, we have to compose it with leader election somehow to start in a state that has special marked agents. And in order to achieve that composition, we use the leader is actually going to run a self-stabilizing population counting protocol in order to reset the whole population and make sure that it gets everyone to a clean state before the simulation actually starts. And that population counting is where the polynomial number of states comes in. Then in the other direction, we show that when we have a sublinear amount of space, we can only compute the semilinear predicates. The idea behind that proof is that we actually show that if the number of reachable states is going to grow with n, it has to grow at least linearly. So if the number of reachable states is sublinear, it actually just has to be constant. There is no middle ground. The next thing we consider are now fast protocols. So here we focus on protocols that have sublinear, preferably polylogarithmic convergence time. And the first problem we consider is population size counting. It's a very natural problem for our model, since our model has the minimal power necessary to actually solve the problem. And it's worth noting too that there is a simple slow algorithm involving token passing. Every agent can start with one token, and they can pass tokens to other agents. And eventually, after enough time, some agent will collect all n tokens and thus know the population size. Now, the algorithm that we show is fast size counting, and it uses a leader. So it will be composed with some sort of leader election. And we can think about the leader is going to be starting with 1 unit of mass, and all of the rest of the agents are going to have a mass of 0. And the idea of our algorithm is that we want to be averaging those masses so that each agent gets about a mass of 1 over n. From this value, it'll know the exact number n. And we achieve that via synchronous rounds of a phase clock. And the idea is that we're only going to average a couple bits of the mass in each round. And at all times after every round, the population is going to agree on a shrinking interval, AB, that contains all of the masses in the population. So at the very beginning, the range is between 0 and 1, and the leader has 1 unit, every other agent has 0. And then our message set is going to be 5 possible messages, 0 through 4. And we interpret those messages as being units of weight. So at the very beginning, the units are in fourths. So the leader has a message of 4 fourths, and the others have a message of 0. Then during each round, we do discrete averaging on the weights. So a 0 meets a 4, they both become 2. A 0 meets a 2, they both become 1. And again, we have the result that quickly we will get 3 consecutive values. So then we can update the interval. The population will learn what the 3 values are, and then redefine the weights. So at the end of every round, we're actually going to partition the interval again into 5 possible weights, and then do averaging, and then update the interval, zoom in, and then redefine the weights. Again, do averaging. Now we have an interval of 1, 2, 3, 3 consecutive weights. So we can update the interval, and now redefine the weights. And we will keep doing this until the interval AB actually only contains 1 possible value of 1 over n. And we can show that it'll take a logarithmic number of rounds. So in this case, at the end of round 4, we've shrunk the interval in half again. End of round 5, it's shrunk in half yet again. And finally, by the end of round 6, our interval actually only contains 1 possible fraction, 1 over 7. So now every agent can terminate and know that the value n is exactly 7. In addition, we can add a slow deterministic backup that will allow this protocol to have probability 1 convergence. And it takes log squared n time because there's log n rounds and each round is logarithmic in length. In addition, we show that we can truncate this algorithm early and actually use much fewer states and instead compute log n. So if we only want an estimate, we can do that with fewer states. On the other side, if we want to know the entire input configuration, we can simply run our algorithm in parallel and count all of the input states. And then we can compute any function we wanted of the input configuration. Now, the next protocol we consider is the protocol for Junta election. And the Junta election problem is to elect not a single leader, but a sublinear, so O of square root of n size junta of agents. And achieving Junta election has been shown to be the key large state primitive for efficient leader election and majority protocols. So they need a large number of states to get a junta, but once you have a junta, there's standard methods for using the junta to run a phase clock and then get other protocols to run fast. So our Junta election protocol actually only uses 1-bit messages, so the minimal possible size message set. And the idea of how it works is it's based on a level variable. This is a similar concept to the related Junta papers. And the level variable is going to have a distribution that decays doubly exponentially. So the probability of having a level above I is 1 over 2 to the 2 to the I. And you can prove that the maximum level achieved in the entire population will be on the order of log n. And we will define the junta to be all the agents that have that maximum level. And the size of the junta can be shown to be O of square root of n. Now, other protocols can simply broadcast the level. And every agent can just send the max level it's seen. And that however, will require on the order of log n size messages. So the key challenge for our protocol is to achieve this using only 1-bit messages. And to do that, we were going to rely on timing of internal counters. So every agent is going to have their level stored locally in their internal state. They're also going to have a counter in their internal state. And they're going to use 2 messages, stop and go. So the counter is going to be partitioned into green regions where they broadcast go, and red regions where they broadcast stop. And at the end of the red regions, there's a special location we call a door. And the way the protocol works is the agents simply count their interactions, increment their counters. However, if they reach a door, if their level is greater than the door, they can simply keep counting. But if their level is less than or equal to the index of the door, they have to meet a green agent before proceeding. So in this case, the agents of the higher level will become green, and they will pull all of the rest of the population with them. Again, we reach door 1, and only the agent at level 2 can keep counting. but then the other agents come along with them. And finally, we get the whole population stopping here at door 2. And now all the agents have learned that the max level is 2. The one agent at level 2 knows it's in the junta. The rest of the agents know they're not in the junta. And we are able to prove that this protocol works with high probability using log squared time and log squared space. And this figure shows an example run from a simulation on a population size of 2 times 10 to the 7th. And here the max level in the population was 6. And we can see from this plot, we have the minimum, the average, and the maximum of the counters of all the population. And we can see that those 3 values stay very close during the entire run. And the counters are, as we would hope, proportional to the amount of parallel time that has passed. And then finally, we notice that every counter stops exactly at our mark of door 6. So first the max, then the average, then the min. Thus, all of the agents learned that 6 was the maximum level, as desired. Also, our simulations actually suggest that this protocol should work using only O of log n time and space. So the parameters that we needed for our proofs are probably bigger than is necessary. Now, the final problem we consider is the computational power of 1-bit messages. So our Junta election algorithm would actually need to use a constant number of messages if we actually wanted to compose it, so to do other computations downstream. But what if instead our entire protocol could only use 1-bit messages? So this is the extreme limit of communication in the model. And what we are able to do is construct a synchronized 1-bit broadcast primitive using, again, only 1-bit messages. In order to achieve this, we need an unbounded internal counter that we partition into rounds of increasing length. So the caveat here is the local state space actually has to grow unboundedly. But if that is the case, we're able to prove that with probability 1, all of the rounds will eventually be synchronized for all future time. So at some point, we can achieve synchronization of the whole population. Once we have synchronization, we can run a 1-bit broadcast primitive. And we build on the 1-bit broadcast primitive to first elect a leader, and then the leader can construct and simulate a Turing machine. So in the end, we show that we can achieve probability 1 Turing machine simulation using only 1-bit messages if we allow an unbounded local state. So in summary, we introduce a new refined model that measures the cost of communication in population protocols. Then we characterize the computability hierarchy of this model with constant size messages. We introduce multiple new fast protocols for the problems of exact size counting and Junta election. And finally, we show how to achieve a broadcast channel and simulate a Turing machine using only 1-bit messages. Now, to sum up, I wanted to call attention to one very key open question from our work. And that is, the Junta election protocol that we proposed has a small but positive probability of failure. Thus, if we were to use that to solve leader election, we would also have a small positive probability of failure. And we actually conjecture that any protocol that solves leader election with probability 1 using a constant size message set is going to still take linear time to stabilize. In other words, the same time lower bound as the constant state model, we think still holds with constant messages, even if the internal states are allowed to grow larger. And the idea for how we think this conjecture could be proven would be based on a density lemma. So you can actually show that all possible producible messages will always appear in the population in large count as a constant fraction in only constant time. So all the possible messages are going to be out there. And we think that using all the messages, we're going to be able to steer the configuration into an undesirable state and use those ideas to show a time lower bound, similar to previous work. And thank you all for your attention, and I would be happy to answer any questions.